Good afternoon, everyone. It's my pleasure to get back to the last session for this week. So let's invite Giuseppe Negro. I'm so sorry with pronunciation.
It's okay. I have the
to
same
give a
problem
talk.
with Indian names.
To give a talk about global solutions with asymptotic self-similar behavior for the cubic wave equation.
Thank you very much. So may I thank the organizers again, because it's the second talk, but I want to thank them again because I'm having really a great time here in ICTS and in India in general. Thank you very much. So this is the last talk of the week, and on top of that, I come here with this with this thing. This is not strictly harmonic analysis. This is partial differential equations, but there are connections with harmonic analysis. And also, I will give a talk that does not assume any previous knowledge of the subject. So I also have few slides. Some are quite charged, but we will spend lots of time on each slide. So you can take your time to read everything. Okay. So this is my attempt at doing a recollection of all the basic theory of the asymptotic dynamic behavior. So the dynamics, sometimes it's called dynamics, sometimes behavior, of solutions to this initial value problem here. So what you see here is the cubic wave equation. Cubic because there's a 3 here, and it's focusing because here I have a plus. I'm going to explain this in a moment. A solution is, I will give a definition, but it's something, it's a function nu that's defined on a time interval I, and the spatial variable x, it lives in the full 3 space, the physical space-time. Cauchy initial value problem because I specify the initial data in this form. At time 0, which is the beginning of times, I give a couple of, a pair of functions. So these 2 functions are specified. And here I use a notation which is very common in the wave equation. It's very useful. And so it's better to start getting used to it. I will use it throughout all the talk. Every time you see a bold phase, this means that it's not 1 function, it's 2 functions, the function and the time derivative. Okay. So here I also have a space, a functional space. This is the homogeneous Sobolev space, the standard one. But since my objects, my functions are pairs, the space has 2 components. One is the first component is just the Sobolev space about the rest. The other one is the derivative, and so I have to lower the regularity one index. Okay, so this is a Hilbert space, and these are the Hilbert spaces in which initial data will live. Okay, so now, what is the problem that we want to study connected to this? No, absolutely not. This is a Hilbert space for the initial data. Yes, you will see here. Good, thank you very much. We will see functional spaces for the solution, but here I only have space-only spaces. So all the spaces that you see here are space-only, CR3. Okay, so why do I care about this equation? This, in my opinion, is a very beautiful PDE. And I'm going to explain why. So, but the problem that I want to study is the asymptotic behavior. So very optimistically, we hope for a criterion that allows us to decide, given initial data are points in some Hilbert space. And we hope, this is very optimistic, but that's what we hope for, to get a criterion that tells us, given this datum, I can tell you what happens in the future or in the past. Asymptotic behavior. Okay. So what can happen? Let me start with this possibility. But every time you see an underline here, underline means one possible behavior. So the first behavior that I want to present to you is the blow up. Blow up means that the solution does not exist for all times. At some point, it ceases to exist. This model here supports blow-up solutions. And this, you can see this very easily, because if you just drop the dependence on space, this is the equation we're starting, right? Suppose you just drop this. So you consider solutions that depend on time only. So now you have an ODE. And this ODE, you can solve it. It's an easy exercise to solve this ODE. And this is its general solution. You can have a plus or a minus here, and this is a -1. -1 because you take two derivatives, and it becomes a -3, right? So -3, -3. It's a very easy exercise. Now, this is a solution, for example, if you take the minus sign here, you have a solution that's defined up to capital T. Okay, so this is the first example of a solution. It's very simple, but it's quite important. This is I, by the way. So the maximal time interval of existence for this solution is this interval here. Okay, and this is an important example. So this problem supports blow-up solutions. Now, here I want to introduce another important quantity, which also gives me the opportunity to explain, give a conceptual explanation why blow-up solutions appear. So this is the conserved energy. And now, since Jotsaroop was asking, let me spell out this definition. So we also practice this notation. So what does this notation mean? It means that I'm taking, here we have a ball, right? So this means take your function and the time derivative and put it in the appropriate space, right? So here we have H1. H1 means put one derivative on the function and 0 derivatives on the time derivative. So this is the first part of the energy, and then here I have just 1/4 of the L4 norm to the 4th of the solution. Okay, so I'm writing this just so that we review this notation here. So this is the conserved energy, and here you see there is a minus. This minus comes because here there is a plus. If I had put here a minus, this would have been a plus. Now, this minus means that these are two positive quantities that can compete together. So intuitively, yes. So yeah, I'm writing absolutely. So this is not a function of t. This is, if you compute this derivative, this is 0. Okay, so it's a constant. I put the t here, so it's a function of the initial data, but it's constant along the flow. And okay, so here what can happen is that both quantities go to infinity. And since there is a minus, they may compensate exactly, which explains why we have blow-up solutions. Okay. To this? Yeah, well, the easy answer is just compute the derivative. And when you compute the derivative and integrate by parts, using the equation, you will see that this is 0. Yeah, this is the easy answer. If not, I should start talking about Lagrangian formulation and all of that. Yeah. I mean, if for the linear wave equation, maybe this is a more satisfactory answer. Imagine there is a 0 here, right? There's nothing here, the linear wave equation. Then this term is conserved, right? Because when you differentiate, this turns into a quadratic form of the Laplacian, and this is the quadratic form of the second time derivative. So this is 0. Okay. Now I have added u cube, and so when I differentiate this turns into exactly into minus u cube. Maybe it's easier to write. Take the derivative and integrate by parts. What you get this. Okay, this is what you should get, yes. Right, and so using the equation, you see that this is, that's it. Great, so in particular, thank you for the question. If I had put here a minus, this would have been a plus. Here, this would have been a plus. So you see, we would have had a completely different behavior because the energy would have been positive. Okay. Also, you see, this is the simplest thing you can do. Thank you very much for the question. Actually, I can say a couple of things. So this is the conserved energy for the linear wave equation. Imagine you want to build a nonlinear wave equation, right? So what you do, you have to modify this energy by adding a term. And what is the simplest term you can add? This is a quadratic. The simplest thing you can do is putting a quartic, because you want an even integer here, so that when you differentiate, you get a positive quantity, actually. You can differentiate without absolute values and things like that. And the next thing, even integer after 2 is 4. Okay, so this is the simplest possible energy, apart from the linear one, that I can build. And this is the simplest possible nonlinear wave equation I can consider. Now, there is a choice to make. There is a minus or is the plus. If I put the plus, I get the defocusing wave equation, but then I don't have blow-up solutions. So this is the simplest nonlinear wave equation that's supposed to blow up solutions. Okay, and this is the reason why I like it very much. And then there are other reasons we will see now. Okay, so this was the conserved energy. Now, local well-posedness. What does local well-posedness mean? Local well-posedness means that for each point in our Hilbert space of initial data, which now we have to choose, right? So we choose S, and if we have chosen a S big enough, bigger than a half, to each point in our Hilbert space, there corresponds a solution. Local, because of course the solution may be only local, so may blow up in finite time. Maybe it's not a global solution, okay? And indeed, it can be that some solutions are not global. And this is the critical exponent. This is the exponent which I will work. If I don't say anything, the Hilbert space will always be H1 half, which is the scaling critical one. Scaling is just this simple transformation. If you have a solution U, you can map it to lambda U, lambda T, lambda X. This is the scaling. We have seen many scalings in this. Okay, so this is a symmetry of the PDE, and it's a symmetry also of this Sobolev space with S equals a half. Okay, so this is the scaling critical space because it's scaling one. So it's a space in which you can apply this scaling without changing the norm. And this is very important because if you go below the scaling regularity, this is very easy actually. I cite Lindblad and Saurabh, but it's an observation more than a theorem. If you go below the critical scaling regularity, you are ill-posed. This is clear because the scaling is going against you. If you take a solution defined in a time interval, you rescale it, so it's defined in a smaller time interval. So it blows up earlier in time. If you have taken small s, the norm of the initial data is becoming small. Okay, so if you put yourself in these spaces here, given a blow-up solution, you can construct another blow-up solution with smaller norm that blows up earlier in time. So this means that you can have arbitrarily small functions in your space that blow up arbitrarily early. And this is clearly, you don't want that. What you want is this. No, it's not easy at all. This is a consequence of the Strickland's estimates. And I will come to this in a moment. No, it's not easy at all. Actually, you can have local well-posedness in H1 with integration by parts methods. But to go down to S1 half, I don't think there's anything else you can do except for Strickland's. of course, right? The S equals 1/2, you can't do integration by parts in a fractional derivative space. Right, so this is another very desirable fact. And we are going to see this in detail in a moment. If your initial data is small in the critical Sobolev space, which is the one I take, my preferred space is, of course, is the critical. And if the data is small, then my solution is global and is asymptotically linear. This is a behavior called scattering. And this is the second behavior I want to present you. Okay, we have seen blow up, and now we see scattering. Scattering means that you are linear in the limit. Okay, it's a very important behavior of nonlinear wave equations. Okay, the intuition is that if you are small at initial time, your nonlinearity is a cube, right? So the cube of a small number is even smaller. So you should not see the nonlinearity here in the small data regime. Okay, you do if you take the wrong node, but if you take a correct node, and this is the right one, you don't. Also, this behavior is stable, which means that if you take a U0 that scatters and you perturb it a tiny bit, it still scatters. This is a very important observation. Now we're going to elaborate on this. And finally, all of this is standard material, textbook material. This is a deep theorem. This is Dodson-Lowry 2015. Actually, this theorem here, I didn't write. This relies on the assumptions that U is radial. And I know that especially Benjamin Dodson is working on this problem because he put the last paper on the archive exactly 1 month ago, end of May, on this problem, exactly this problem. And I know he's working at removing this radiality assumption. I don't know if he succeeded yet. I checked the literature. I don't think he succeeded yet, but it's widely conjectured that this should be true, as I wrote. So what's written here? If your solution is bounded in the critical Sobolev space, then it's global and scattering. Okay, this is important. This is an important thing. It's not the same for all nonlinear wave equations. And this is a kind of ODE behavior, right? The ODE, if you have an ODE and you are bounded, you are necessarily global. Okay.
Is there an additional C?
No. By this I mean just any constant. So this is what this means. If you are bounded, no, it's not a universal constant. No. This can depend on you. So
arbitrary data.
yeah. So if you are bounded, then you are global and scattered. Okay, bounded on all your lifespan. Okay. Otherwise said, the only way, let me see, global and scattered. Yes. Sorry, I was going to say something even more confusing. So that's it. This is if you are bounded, you are global and scattered. Bounded in this space. Good. Okay. So this was just an introduction. Now, before going into my theorem, I've thought of proving this. This is a digression. So this means you can ignore this slide and the next one, and the content of the talk is the same. And it's also textbook material. But I thought that maybe this audience could enjoy this. I would like to prove this scattering is stable. Because here we practice with using this equation, the nonlinear equations. And we also see the importance of harmonic analysis in these things. Okay. So here we have the Strickers estimates. We have actually seen these estimates in my previous talk and also in Diogo's lectures, because these are essentially the restriction estimates to the cone. So let me start from the beginning. Let me consider a linear problem. This is the linear inhomogeneous equation. Right? This is the wave equation, but with a source term. You can write the solution like this. This is why, here notice I'm putting the bold on S, right? So S is this operator. I put the bold because I want to consider the function and the time derivative at once. This is really, the wave equation is really, the variable of the wave equation is really two variables, function and time derivative. And you can see, if you differentiate this object twice, Yeah, you can see that it solves this equation. It's quite an easy computation that you can do, right? So this solves the homogeneous PDE, and this solves the inhomogeneous PDE with zero initial. This operator here is exactly the extension operator on the cone, this S. And this estimate here, so that this operator is bounded, maybe it's a good idea to write this down. The fact that this operator S is bounded from H1/2 into L4, this is exactly the Fourier extension to the two-sheeted cone. Right? This surface which we have seen several times during this week. And then you have to use duality. So this is one inequality. Then you can dualize it, and you get this. This is a Hilbert space, right? So the dualization stays here. And then you can apply the SS star argument. And now, turns out that with the twist, not exactly, unfortunately, this operator SS star is exactly this guy. Not exactly, it's this guy integrated from -infinity to +infinity. And so up to a lemma due to Christian-Kiselev, this inequality here, you see L4 bounded by L4 thirds, is the statement that this term here is bounded from L4 third into L4. Okay, so this L4 third comes because of this duality. And this S star here is responsible for this bound. So this term is bounded by that term. You see here you have the energy goes to the left. Okay, so I'm sorry that I haven't found a way to make this nicer. Just the numerology, just as an idea of the numerology. So this is the numerology which we saw last time, and it's responsible for this L4, this H1/2. And then these dualities, these θ star arguments, are responsible for this H1/2 and this L4. Okay, and this is the inequality has been proven by Strickers in the 77. This formulation, I've taken it with Kiel and Tau. They put also this term here. Okay, of course, Kiel and Tau prove a much more general estimate, but I only need this. And now, so this is harmonic analysis. This is essentially the Fourier extension to the cone. And this is the main ingredient in all the theory, the basic theory that I presented during the previous slide. Everything I said, the local well-posedness, apart from blow up, of course, but the local well-posedness and the scattering, all are consequences of this. And let's see the scattering. So why is the scattering is stable? This is something that I think deserves to be better known. This is a deep statement in scattering theory, even though it's very easy for us, because we can prove this scattering criterion here. So scattering at +infinity is the same as this norm, the L4 norm that comes from here, being finite. Because once you have this, notice that your equation was well-posed. Well-posed means not only that you exist for all initial data, it also means that you are continuous with respect to your initial data. So this is a continuous, now U is a solution to the nonlinear wave equation, and this norm is a continuous function of the initial data. So if I take a solution that satisfies this, and I perturb it a tiny bit, it will still satisfy this. You cannot, if you have a finite norm, you change it a tiny bit, it still is finite, right? So this is it's a standard fact, but it's quite deep in my opinion. And it's quite amazing that something like this, something is completely dynamics, on the dynamics of the nonlinear wave equation, is exactly a consequence of restriction theory. And now let's see the proof of this criterion. So okay, so this is what I just said. Oh, no, sorry. So this arrow, this implication is easy because scattering means that I am essentially a linear solution. Okay, so I chop this interval in two. On a finite interval, this is finite, obviously, and then on the tail, I am essentially a linear solution. But for a linear solution, I see this, okay, the L4 norm of a linear solution is finite. So if I scatter, I am finite. And let's see the reverse implication. This is still a digression. Recall Strickland's estimate, that is essentially a conic restriction. So this is exactly the formula of the previous slide, this one, only that I factored ST. This is a group, so I can do this. I can factor this ST here. It's a group of a one parameter group of linear operators. And now what happens? This integral, if this norm is finite, this integral is convergent because it's Cauchy. How do you prove an integral is Cauchy? You take the difference from tau 0 to tau. Now I artificially insert ST. I can, because this is a one parameter group of unitary operators. Okay. Now this, I can put it inside. And now this is, what is it? This is exactly this operator here. So I can use this bound. This is bounded by L4 terms, right? Because this solves the linear wave equation, inhomogeneous, that vanishes at tau 0. So I can bound it by just F. And F for me is U cube, and the numerology is good. I end up with this. Now, this norm is finite. So in particular, if I make T0 and tau and T close together, this integral is small, arbitrarily small. So this is Cauchy, it's convergent. And if it's convergent, this means that U is essentially the linear propagator of this function here. Okay, so we have proven the scattering criteria. I think it's quite amazing that we can do something like this in 2 slides in 10 minutes. If you go, I'm not a historian, but I went a bit into the literature. So for example, I was reading a book by Strauss, 74, nonlinear scattering theory. And it's a book all devoted to this problem. 74, so it's right before Strickland. And he cannot get, it's a wonderful book, but he cannot get to this level of regularity. Of course, because he didn't have the Strickland's estimate. Okay. So I think this is a very remarkable fact and a very big success, historically a big success of harmonic analysis. Sorry? It's a bit more complicated. Yes, H1 and this statement. He has this argument here. The statement is a bit more complicated. I don't really understand. Yes, absolutely. T goes to infinity. And the integral is convergent as T goes to infinity. Okay, so back to, so now the talk can start. This is again, but now we have practiced a bit with all of this. Okay, so we know a bit what's going on here. Also the local Wilposen, for example. Local Wilposen is a consequence of the Strickland's estimate because you do a fixed point here. Good. So what is my result, our result? The result I have with in collaboration with Thomas Duquesne from Paris Nord. I forgot to say it in the very beginning. So let's, instead of stating it, let me draw pictures of it. So basically, Thomas and I solved the cubic wave equation almost explicitly with this explicit family of initial data. Right, so capital X and capital Y are points, are numbers. And for each one of these numbers, so for each one of these points in this diagram, we can solve the PDE and tell you exactly what happens in the future. Okay, so it's a family of explicit examples to the wave equation, to the cubic wave equation. And we found that there is a threshold here, this function, this blue function. This is a numerical plot, actually. I did this with a numerical computing. This function is almost explicit. You have to solve an integral equation. So up to solving an integral equation, you can plot it with arbitrary precision numerically. And we have a region here in which if you solve the equation with this explicit data, you scatter in the future. This is for t going to plus infinity. So here you scatter. You see, close to the origin, but also far away in this tail here, you scatter. Here you blow up in finite time, also here. And exactly on the boundary, you have a hybrid behavior, which is not of the type of the first slide. It's not neither blow up nor scattering. Okay, it's global, but it's not scattering. And if you do then the full, so in the future and in the past, that was only the future. Then if you do future and past, unsurprisingly, you see a symmetric picture in which you have various behaviors. Here you scatter. You see, scattering is stable, so you should have a neighborhood of the origin scattering. And indeed, this is an open neighborhood of the origin. And then you have all the various other possibilities. In particular, these 4 points are global and non-scattering, both in the future and in the past. Okay, this is a nice, in my opinion, important observation. Let me check the time. So the topology that you see in this plane, so the norm of this plane, the distance from the origin, is exactly the critical Sobolev norm. So I like to think of this result as, you know, we want to study the big problem of, given a point in my Hilbert space, this Hilbert space, given a point in my Hilbert space, can I tell you what is the behavior of the corresponding solution? This is very optimistic. It's very difficult to get something like that. But at least here, we are taking a plane in our Hilbert space, so a cross section. And in this plane, which is this plane with the right topology, we can tell you everything. Okay, so at least it's a picture. So in the first slide, we had lots of information, small data scatter, big data may blow up, may not. This at least is a picture of that to begin with. Moreover, all our solutions are finite energy. This is a remark I will explain later. Energy is this. And it's not obvious that it's finite. If you solve the equation in h1/2, you only have 1/2 derivative. So this can be infinity. But these solutions are also finite energy. And also, and perhaps more importantly, we are seeing here a new behavior, which is unstable, because if you are on this line, you perturb a little bit, you end up either on the blow up or on the scattering region. So we see a new unstable behavior, and we can characterize it precisely. Okay. So this is the result. This picture is the result. And now I'm going to give some more questions so far. Yes. No, that's just a fact of the picture. No. This continues. You can imagine that this picture continues to infinity. Yes, they never cross. They are asymptotic to each other. Yes, absolutely. It's like, maybe you see it better here. It's like this is kind of, I don't know how you call it, eye with two very long eyelashes. Will go down to infinity, and this gets thinner and thinner, but there is always something here. Yes. So the 2 is just where I plotted it, not it's immaterial. Okay, so now let me give a bit more details on these solutions, and now I want to focus on the threshold solution. Yes. Yes, this. I will tell you where this comes from.
If you start with this,
this is the behavior you get, yes. So if you, for example, if you put here x equals 1 and y equals 0, so you are here, right? The corresponding solution, which is not of this form, of course, this is just the initial data. Then you have some solutions, and I can tell you that it scatters. If you put here x equals 10 and y equals 0, so you are here, I can tell you that you blow up in finite time. And if you are exactly here, you are threshold, then this is what we think is interesting, because it's a new behavior that you see. It's neither scattering nor blow up. So it's the third type.
At that line.
Exactly, beta. Yes, exactly. This question, I will answer this question in a moment. But to begin with, you can see that it's both finite energy and in H1 half. Where is it? Yes, yeah. So both the important quantities, which is this one and this one, are both finite. Okay, and so by Strickland's estimate, also the L4 norm is finite. So all the norms which we have seen, the L4 norm in space-time, all the norms we have seen are finite with this class of data. Okay, so we are really solving the equation in the right functional space. So this is a first thing. Now, the threshold solutions, of course, we have studied them because we need to give as much information as possible on this new behavior, right? Which is global and non-scattering, right? And we call this behavior a threshold. Of course, finding threshold behaviors is one of the big problems of PDEs because it's like this. You have a certain stable behavior, scattering, then another certain stable behavior, blow up. This is not proven that it's stable, but it should be. And then at the threshold, there should be something unstable. What happens at the threshold? This is one of the questions of evolution PDEs. Now here we give a partial answer. We conjecture that this is the threshold behavior. We will see, now I'm going to say that this is in accordance to existent conjectures. And now here we characterize the behavior precisely. So here, this is a representation of space-time. Our solutions are radial because initial data is radial. So I only need to plot here the radial coordinate and the time coordinate. This is the so-called wave cone, this line. And inside, roughly speaking, our solutions are inside the light cone, they are of this form. This form, which is this. Right? So they look like these blow up. Unsurprising. There are conjectures on blow up that this should be quite general. I'm not going into that, but there are several conjectures. Papers. Okay. I'm not going to. But here we see this behavior. Outside the light cone, we see essentially linear behavior, scattering. Scattering means asymptotically linear, right? So I can use this word here. So here we see this scattering. Notice that this scattering is in H1, not in H1 half. This is no accident. No accident, why? Because this solution is not in H1 half. Right? So it is maybe, if you chop it on a finite interval, maybe it is, but if you take it everywhere, it's not, because it's a constant. When you differentiate it, the derivative, it's also a constant. And H1 half, this is a technical remark that would be, I hope it's not too. So the H1 half norm, which is the critical one, so what is it? You have a negative order derivative on the time coordinate. So if I put here something that is essentially constant, remember, what is this? This is take the Fourier transform and put here this weight, right? If I put here something that is essentially constant, this Fourier transform is concentrated at the origin. And so this denominator will make it blow up, okay? What I mean is that you can never have this scattering in H1 half. Because here at the boundary, you are guaranteed to have problems because you have you have something coming from here that has infinity H1 half more because of this. Okay. I'm saying this because when I gave this talk in Lisbon, Georges Dumont immediately jumped on me because of this. But no, it's not a limitation of the method. It's really that you can't have H1 half here. Okay, so here you are asymptotically linear. So here you have the scattering behavior, here you have the blow up behavior, and our threshold solutions, unsurprisingly, maybe unsurprisingly, are a mixture of the two. That's what it should be, right? We have precise bounds, both inside and outside the light cone. And then here, look, I think this is a very nice observation. I mean, I was amazed to find this. Recall, what did Dodson and Laurie say? They say, if you are bounded, you are scattering. Here we are global, but we are not scattering. So we should be unbounded. And indeed we are. We are unbounded logarithmically. We can even give you the precise bound. Okay. So our solutions are unbounded, and we can even give you the precise rate, which begs the question, is this rate optimal? I believe it is. So if there is a possibility to sharpen this result, but this is just a conjecture, that this can be weakened. Instead of imposing that solutions are bounded, you can require that they blow up, that the norm is less than a log, and then it should be scattering. And this is kind of a more technical remark. But in any case, this is an illustration of the Dodson and Laurie theorem. Global solutions must be either scattering or unbounded, and this is unbounded. Okay. So this is a bit of a technical thing, but this picture is an illustration of the behavior of our threshold solution. Now, let me compare this result with the existing conjectures. This is the conjecture of Bizzoni and Zenginoglu. This is a numerical one. They conjecture that the general threshold between scattering and blowout should be given by a codimension 1 manifold. They don't specify where. So the natural thing would be a codimension 1 manifold in the Hilbert space of initial data. That would be the best possible result. So a manifold of codimension 1 of global solutions that satisfy this bound. And indeed, this we do. That's exactly here. We have something to say on the error term, but that's not really important. Okay. So our solution fit into this conjecture, which is numerical and quite widely accepted. And then there is Zenginoglu further worked on this with the Roland Doninger, and he did found a manifold, but you see the result is it's not codimension 1, it's codimension 4. It's a bit technical, you can ignore this. And of global non-scattering solutions which satisfy this bound. Again, so what is this result telling you? They are these solutions inside the wave cone, because look, this region is shaped like this. So it's inside the wave cone and far from the boundary. They are close to square root of 2 over t, exactly like our solutions. And also the numerology is correct, because if you put here, they have L4 here. If you put here 4, here you will get a half, 1 minus 1, t minus a half. Okay, sorry to going back and forth. This is it. Okay, so our solution also agree with this numerology here. There is I don't know if you can call it an issue. I mean, something remarkable about this is that their solutions are not finite energy, and they are also in other initial value problem. So it doesn't really fit into the framework of the Cauchy initial value problem. They solve a hyperboloidal initial value problem. Okay. So we consider this as a step toward the proof of this conjecture. And we consider our proof as a further step towards the resolution of this conjecture, because we have finite energy solutions and solutions to the Cauchy initial value problem. Okay, so this is my I propose this comparison to the existing conjecture. And now, let me finish by telling you how we construct these solutions. And here again, I'm going to use the conformal invariance, which is something I also used in the previous talk. What does conformal mean? So conformal means that preserves the form, so that preserves the angle. Right? So here, this is a bit of a detail. The angles I want to preserve are not the Euclidean ones, because I am in space-time, and the geometric structure of space-time is not Euclidean. Albert Einstein tells us that space-time is not Euclidean, it's Lorentzian. So this amounts to put here a different scalar product that is not Euclidean one, is a non-positive definite one, a certain scalar product. Anyway, if you have a map that is conformal, so that maps a map of Minkowski spacetime into itself that preserves this scalar product that I just mentioned, then you can define the conformal factor. Conformal factor is just, you see, is the determinant of the Jacobian is a measure of dilation of volumes, right? So 4-dimensional volumes. And I want to take the fourth root, so I have a measure of the dilation of length. Okay, so the conformal factor measures how I am dilating length at each point. It's a function conventionally called omega. And here we arrive at the fundamental property of the cubic wave equation, which is the second reason why I like this problem very much. The first is that it's the simplest nonlinear wave equation that supports blow-up solutions. And the second is that it's conformally invariant, which means if I change variables in this way, conformally, I pass from the tx variables to the tilde t, tilde x variables, the D'Alembert changes like this. You might have seen, I mean, this is a very famous formula. Maybe you have seen the Euclidean version of it, which is the conformal, I mean, if you have a conformal map of Euclidean space, the Laplacian changes nicely in a very similar way. The D'Alembertian changes like this in the Lorentzian case. And now you see that the numerology is right. So if I do a conformal change of variables, I get an omega cube coming here. And here I have an omega minus 1, so I can change u. Right, so u changes like this, takes an omega cube, and the two omega cubes simplify. So the equation changes into itself if it undergoes a conformal change of coordinates. Okay, because there is this simplification. This is the magic, 3 and 3. If I put here 4 or any other number, this will not simplify, and I will get another equation. Okay, so this is the reason why this equation is called the conformal wave equation. And this is what I was saying. So conformal wave equation is a reformulation of this. Now, I want to do this change of variables, but with manifold valued maps. Instead of mapping Minkowski into Minkowski, I want to map Minkowski into some other Lorentzian manifold. I only need one, which is the one I was talking about on Monday. So R times the 3 sphere, that cylinder that I had before. And this I'm not going to explain, because this is the best explanation of this lies in geometry, unfortunately. And so it's a bit complicated to give it in a couple of minutes for me, at least. If I map into manifold values, I have the same formula here, only that instead of this Laplacian tilde, I should put Laplacian plus 1. So here I have a plus 1 with this manifold valued conformal map. Okay. So this plus 1 comes from geometry. And what is the transformation? This is the same slide as the other. This is the conformal map that I will use. I map conformally Minkowski space-time into this subset of the four-dimensional cylinder. Okay, here, this radial variable on the sphere is the angular variable, the distance from the North Pole. The equations are the same we have seen the other day. This map is conformal. This is a beautiful observation of Sir Roger Perot. And now, let me finish. I think I have, yes, I can finish this. So why can I construct solutions to the cubic wave equation using this observation? Because I can do exactly this. So here I neglect, this is, by the way, most of the times, this is how you construct families of solutions to some PDE. You just neglect some of the variables. Here I neglected space, and I ended up with this ODE, which gave me this family of blow-up solutions. And that's all I can do here. There's nothing more I can neglect. But if I do the Penrose transform, which is a manifold value, so here I have a +1, right? Now the PDE I get on the sphere is this one. And if I now neglect the space variable, I am left with this ODE, which is much richer than this one. So this ODE, this is the general family of solutions for this ODE. But this one, this is called the Duffing equation, as much more diverse solutions to begin with. Also, there is another thing. Here, I'm mapping my space-time into this triangle here, and I'm neglecting space. So my ODE will be defined in a strip like this. So ODEs, you know from basic ODE theory, the solution to an ODE is defined in the maximal time of existence. Right? So this is the maximal time of existence of the ODE. The ODE lives in this conformal space-time, and I have plotted here, I put back these two lines in the physical space-time. So my solution in the physical space-time is going to be defined in this region here. That this is if T plus and T minus lie inside of the triangle. If I make T plus go up, this hyperbola here will go up. And if I make so that T plus is exactly here, this hyperbola will lie exact at infinity. And these are going to be the threshold solutions that I've been talking about. Okay. And if I make this go a lot up, then my ODE will maybe blows up, but it blows up too late. In the physical space-time, I see no blow up, and so I see scattering. Okay. So depending on this, of this function here, this is an explicit function, this is an integral. This is the ODE time of existence is a well-known thing. It's an integral depending on the initial value of the ODE. So depending on this function, I can construct solutions with any prescribed behavior. And if I put the blow up exactly on pi, I see the threshold. Okay, so this is how I construct the solution. And then I have to do all the estimates and all that. But this is the idea. This picture is the idea. Okay, so this is the end of my results. I think I have 1 minute and 20 seconds. So this slide, it's a bit, the talk ended, but so looking at the last talk of Diogo, I've thought of adding this. This is another slide on something that is not my research, but I think it's good to know, to compare this result to other results existing in the literature. So what happens for other nonlinear wave equations? So here, there is a peculiarity. Yeah, we are studying this equation with p equals 3. The only other value that is really remarkable is p equals 5. In this case, you have this family, not this stationary solution. This is exactly the kind of solutions that Diogo was studying in the very last part of his talk. This is a solution to the elliptic part of the wave equation. And for the quintic wave equation, which is the only one, because of this very nice identity due to Pocozayev, now not going into this, this is the only PDE, the quintic is the only PDE that admits stationary solution, the only nonlinear wave equation that admits stationary solutions. And then you have a very deep result, which is the solitary solution. So for the quintic wave equation, this is the threshold behavior. So you see, it's completely different. The dynamics is completely different. Stop. That's it.
Do we have questions from online audience? No. Okay, any other questions from audience here?
So you started with the H dot. That
Do you mean the Sobolev spaces?
yes.
Yes, H dot, yes.
Okay, but you always work with the H1/2.
Dot.
Oh, that contains already dot, is
There
it?
is a dot, yes. It's just notational thing. Yes, sometimes people put a dot here, but
Okay, so it's not the, I mean,
it's homogeneous Sobolev space because I want the scaling. So yeah, the scaling is important for me. So the focusing case has another completely different dynamics because here you have a plus. So this is conserved, and so all solutions are bounded. You see, because you can just dump this. So the energy controls the norm. No, it's not. There are several questions. Actually, not. I mean, you control the H1 norm. Yes, sorry. You control the H1 norm. For the quintic, I'm sure that all solutions are global. And now for the cubic, I have a PDEs. There is a problem that you have to remember. Main is, these guys surely have said a lot of stuff about it. So you should check these guys' literature. And I believe that all solutions are global and scattering. Yes, but you should ask them. So no, good question. So even powers of view, you have here. So you see this computation. This is very nice because here you have u to the 4. No, if I had to consider even power, here I would have u to the 2n plus 1 with the mod. So this, it's difficult to do algebraic thing because we do exact stuff. Yeah, solutions are real. Solutions are real, yes. But that's the same. I mean, in any case, you have an absolute value. So it's a bit doing something so exact. Forget about it. And also, I need the cubic wave equation because, sorry to go back and forth. I need the cubic wave equation because of this. So I need that these two guys cancel exactly. I put a 4, they're not going to cancel, and then forget.
Does not exist. Like,
Sorry?
I see that all this analysis now basically work with mod u to the p minus 1 u type of non-linearities.
Yes.
I'm wondering if there is some class of non-unity where you can say that no, the solution does not exist. I mean, at least in the space of interest, you know, like.
I don't really know the theory about general nonlinearities. The only interest example I know Where you don't have a power here is the sine God, or you have a sinus, a sine U. That's the only interesting example I know. But I don't know how to answer your question. So you are asking for a completely ill-posed equation.
At least somewhere we can say that does not exist solution, say in spaces of interest like subler space or
I don't really know how to answer this. Yes. Okay. Yes. This is easy. Yeah? I'm citing Lindblad and Sog, but that's really easy. Just a scaling thing. Yeah. Maybe there are examples that are ill-posed on every subwheel space. Can be. I mean, PDEs are crazy.
Any more questions? If there are no questions, let's thank the speaker. And this is the final talk, and hence we would like to thank once again for all the
Oh, thank
interactive
you.
sessions we have had this week.
Thank you.
So thank you once again.